Okay, hello everyone. So let's continue our story about GMRS. Okay, so this is the outline of today's lecture. So we will do a little bit of revision on the standard GMRS, and then we will talk about another way to implement GMRS, which is called restarted GMRS for large problems. And then we move on onto a different topic called preconditioning. Okay, then that's all the stories, the plans for today. Okay, then let's do the revision. So in the last lecture yesterday, we considered GMRS, use GMRS to solve our linear system AX equals to B. What it does is to minimize this residual, okay, the norm of residual norm from the linear system. And we use the Arnoldi decomposition. Okay, after the decomposition, you get this VM and you get HM bar. And then you can compute RM norm in this way. And then what we really does is basically we reduce our n-dimensional problem. Remember this RM is big long vector, okay, size of the full problem. And then on the right-hand side, this is become an m-dimensional least square problem, because AHM bar has n+1 rows. Okay, so this is the like system that over-determined. So then we can solve this Ym. Once we have Ym, our approximate solution in this Krylov subspace just can be computed as Vm times Ym. Okay, so that's the idea behind GMRS. And then today we'll continue on the story for GMRS. Right, one more slides about GMRS. This is about the convergence, right? We have this inequality that determines the convergence of GMRS. Basically, it's saying that the relative residual depends on the condition number of X. This is our eigenvector matrix, and the distribution of the distribution of the eigenvalues of A. Okay, and see how quick the magnitude of this PM, this polynomial GMRS polynomial how quick it can go down over the spectrum of A. Okay. And we also did a few examples that we see that we don't like small eigenvalues, especially those ones that on either side of on the origin. Okay, so we don't like those ones, and we like clustering of eigenvalues. Okay, but you asked me, okay, right? So but we can't. If I have my AX equals to B, then that's my problem. I can't just shift and change my eigenvalues, right? I can't just shift the origin. But there is some ways. Okay, there are ways that later on we will talk about preconditioning to achieve a similar effect. And for now, let's talk about restart GMRS, okay, which is a different aspect to implement GMRS for large problems. Remember that we build our orthonormal basis, V1, V2, Vm for the Krylov subspace, and we're growing. We build this one vector at each iteration. Okay, keep growing our vectors, and each basis vector is of dimension n. Okay, it's a big long vector, the size of the full problem. So here the storage. We are thinking of a large problem. Then the storage cost for our VM that matrix, you know, it's become it's order m times n. It's a dense full matrix. Okay. So for large m, this easily the dominant storage cost. Okay, much more requires much more memory than a typical sparse matrix. with order n non-zero. So think about your matrix A from like 5-point finite difference discretization. You have 5 bands, okay, and you rotate that. That's count like five columns in Vn. So as soon as your M, your Krylov subspace size is bigger than 5, then this Vm, remember, this is for large problem, so your M is certainly bigger than 5. So this Vm gonna be huge, okay, requires lots of memory. And furthermore, a typical sparse matrix vector product requires order n operation. So using each entry of A once. Okay. But the cost of orthogonalizing the next Krylov subspace, Krylov basis vector against all the previous ones is order m, and then you do this m iteration m times, so that become order m square work. So just doing the orthogonalization itself, that require order m square work. Okay, when your m is large, so again, this easily become the dominant runtime cost. Okay, so for large problems, two things that's on your mind that make you worried, right? So the memory and the runtime. Okay. So let's see how the restart GMRS can help. Okay, so for reasons of storage limitation or runtime consideration, there might be an upper limit on the size of our M. Okay, so it's quite possible that our GMRS cannot converge within a limited M iteration. But if that's all you can afford, then that's all you can do. Okay, so the idea is to use restarting. Simply take M iterations that you can afford and then compute that approximate solution XM as usual, and then use this as the initial guess for a new cycle of GMRS. Use this one as a new initial guess for the next cycle of GMRS. Okay. Until you achieve the desired tolerance. Yeah, so this is this method is called the restarted GMRS and denoted as GMRS M. So N here means you restart how many every M iterations. Okay. All right, so here, remember I talk about initial guess. Okay, we never talked about that before. So how do we set up initial guess in GMRS? So remember that for the standard GMRS, we find our solution in the Krylov subspace, and this is count as taking the initial guess as 0. So it's a vector of zeros. So if an initial guess is available, then we can instead use the affine space. So XM is computed as X0 plus, okay, something in the Krylov subspace, and then let our initial residual is just B minus A X0, that's the initial guess, and then set X equals to X0 plus some delta X, okay? So this delta X is gonna be the one we're gonna solve, okay? So we have the original problem, AX equals to B, and now X is written as this one, X initial guess, and then plus some like a correction, okay? And then equals to B, so then we move this A times delta X to the left-hand side and then put the rest to the right-hand side. And then so this becomes A delta X equals to R0, so the initial residual. So now, okay, we run GMRS on this new problem, A delta X equals to R0, and then calculating this delta X in this new Krylov subspace. Okay, so it's built for A and R0. Okay, the vector is R0. So now our XM, our approximate solution, is X0 plus this delta XM, okay, from the GMRes. And then you just use this XM as the initial guess for the next cycle of GMRes. Okay. So now let's have a look one example. So this is me just taking a matrix. This is a so and then take some right hand side vector B, and then I set my tolerance to be 10 to minus 10, and with a maximum number of iterations 1,500. And then I will say, okay, so let's try, we restart every 40 iteration. Okay, and later on we try 80 and 120. Let's see the effect of restart. Okay, and then as usual, I just use the MATLAB's built-in function GMRes. And then we plot the relative residual against the number of iterations. So what we see here is that, okay, so the blue curve is my GMRes 40, restart every 40 iteration, and then yellow is for 80, restart every 80 iteration, and the green is restart every 120. And for comparison, I also did the just full GMRes, okay, with no restart. So we see that, okay, definitely if I restart too early with a small m, then my convergence is slow, okay, it is slow. So my full problem, I can reach convergence, I can get my tolerance around like 340 roughly. And for the GMRes 40, then I have to take like 1,300 iterations to finally get down to the tolerance I want. But on the other side, it's interesting that notice that actually the runtime, this one is winning. Okay, GMRes 40 is actually run faster than compared to the full GMRes. Okay, that's interesting. It's only like it takes 1 second, and the full GMRes takes 2 seconds. It's almost half the runtime. So this is because you only solve m equals to 40. It's so easy to compute and to orthogonalize. And then for the full GMRes, you remember you build your m up to like 300 something. So each time when you have to adding one new vector, and you have to orthogonalize against all the previous ones. So every iteration, it takes longer and longer to run, okay? So the problem becomes bigger and bigger as the m increase. That's why it's actually the full GMRes takes longer than GMRes restart at every 40 iteration. And just for fun, I did the 80 and 120 as well. Okay, these two also pretty good. So it's yeah, I mean, in terms of runtime, it's also pretty fast. Okay, it's still quite small compared to the full GMRes. All right. So what do we learn from this GMRes, restarted GMRes? So the first point is that doing this restarted GMRes, we are able to keep the memory requirements bounded. Okay, we use small m. Okay, and it's also it limits the orthogonalization cost. Yeah, so because your m is small, and then this is the orthogonalization cost is order m squared. So when m is small, this is quite a doable, and when m is big, then this become a main runtime cost. Okay, but there are some serious consequences, right? We lose optimality across the cycles because each time the residual is only minimized within each cycle. Okay, and whatever progress we have been made to localize those trouble eigenvalues is lost. Okay? So each time the cycle starts over from scratch. But we hopefully we get an improved initial guess to contribute to the convergence. Yeah, the rate of, as you see in the previous example, the rate of convergence may be seriously deteriorated compared to the full GMRS. Okay, so for M is 40, and yeah, it takes a while. I mean, in terms of iterations, it converged. But if I start like a GMRS 20, ooh, I don't know, it might, yeah, you can try that yourself, and then you can probably gonna take a long time to converge to the tolerance to the desired tolerance. Okay. So that's the key point about restarted GMRS. All right, so now move on to our new topic, preconditioning. So in the last lecture that we saw, the eigenvalue distribution plays an important significant role in the convergence of GMRS. Okay, we saw quite a few examples. And we also see that, remember, I played around just with my original AXB. I just add I or add 2I. You see that the eigenvalue distribution has been significantly improved by doing that. Okay, and so the convergence rate has been improved by doing that. But you say that, okay, that's cheating. I can't just change my problem. But there are ways, okay? That's called preconditioning to achieve a similar effect, okay? Right. So the idea of preconditioning is that we want to find a matrix M, okay, which is our preconditioner, which approximates our original matrix A, coefficient matrix A, in some sense, and whose inverse, M inverse, is also computationally efficient to apply. Okay, so here is our original problem, AX equals to B. And if we multiplying by M inverse on both sides, so our problem becomes M inverse AX equals to M inverse B. Okay. So now the convergence will depend on the properties of my new matrix M inverse A, okay, instead of the properties of the original matrix. And if we can choose, we choose a good preconditioner, then this matrix M inverse A will have a much more favorable spectrum. Like for example, in the example we see last time, that we remove the small eigenvalues, and we may have achieved some clustering of eigenvalues. Yeah, that would be great. If we can do that, then this transform, this called preconditioned system can be solved much more quickly than compared to the original problem. So that's the idea. Okay. Okay, let's take another look of our preconditioned system. Okay, so for this idea to be useful, we need to be able to compute the operation represented by M inverse efficiently. Okay. So let's think about how do we choose my precondition. Okay, so if M is very closely approximate A, so then M inverse A is roughly like A inverse times A. So it's almost the identity matrix. So if it's too close, M inverse is too close to A inverse, that means applying this precondition may be as hard as solving the original problem. So nothing has been gained, okay, if M inverse is too close to A inverse, okay, nothing to be gained. On the other side, if my M is just identity matrix, then okay, then my preconditioned system is the same as the original problem. So again, so nothing achieved, right? So we need a matrix M that strike a balance between these two extremes, okay, somewhere in between. Okay, so M has to be somehow effective at improving the spectrum, improving the spectrum of M inverse A, but not too expensive to calculating an operation like M inverse times a vector. Okay. So the idea we describe here is called left preconditioning. Okay, you multiply M inverse on the left of matrix A. On the other side, that we can also multiply the preconditioner on the right, okay, to implement right preconditioning. So this time we have A times M inverse M times X equals to B. And we let U equals to M times X. So our system becomes, preconditional system become A M inverse U times B. Okay, and then we solve for U. Once we know U, then we need to compute M inverse U. That's why I keep saying that this M inverse times U has to be can't be too expensive to compute. So it needs the action of M inverse has to be computationally efficient to be computed to apply to the vector U. All right. So now you think, okay, so that just look the same. You multiply a matrix M inverse on the left or on the right. Okay, so the difference is more than cosmetic. Okay. So when we do preconditioning on the left, the residual vector, okay, the residual vector whose norm is monitored for convergence in GMRS, look like this one, right? Okay, so let me write down the precondition system. On the left is that you multiply M inverse on the left of A. So your system become M inverse A times X equals to M inverse times B, right? So for this precondition system, the residual is M inverse B, the right-hand side vector, minus M inverse A times X times the approximate solution, right? And then you take M inverse outside, the inside bracket, you have B minus AX. Yeah? So this is the true residual, right? True residual. So it's equals to M inverse times the true residual of the problem. So here, if M inverse is quite close to A inverse, okay, then this left precondition residual approximate the error actually. So the error is just the exact solution X minus your approximate solution. And X is A inverse B and minus XM. So take A inverse outside, inside bracket, you have B minus AXM. Okay. And then this is your Rm, right? This term is your Rm. So A inverse times Rm. And then if they are very close, M inverse is very close to A inverse, then this is approximately like M inverse times Rm, which is your residual, the preconditioned residual. Okay. But if M inverse is not very much like A inverse, then it's not very clear that what this left preconditioned residue really represent. But it is the residual that being monitored in GMRS in the MATLAB function. Okay, so it's monitoring the relative residue of this preconditioned system. Okay, on the other side, this is our right, for the right preconditioning. the residue is unaffected. So let's have a look. So if it's our right precondition system, then we have our A M inverse M times X equals to B, right? And we let MX equals to U, right? So this becomes A M inverse, sorry, just a sec. U times B. Okay, so you're solving this precondition, right precondition system. Okay, solve for U, and then once you get U, then you do M inverse U to compute X. So the right preconditioned residue is B minus the right-hand side vector minus this AM inverse times UM. And this equals to your UM is M times XM, right? And then this part, this M inverse M, that's just identity matrix. So you end up with B minus AXM, which is the real residue of the system. So that's what we're saying, that the residue from the right precondition system is actually the representing the true residue. Okay, but yeah, just to keep that in mind, that MATLAB inbuilt GMRS function actually implement left precondition. Okay, so the res vector that's coming out from the GMRS is the left, the norm of the left precondition residue. Okay. All right, so now let's have a look at a few classical preconditioners. Yeah, so for this lecture, we're gonna use yeah, the same example Tim did used in the last lecture. It's called Sherman 5. It's a matrix from a real problem in oil reservoir simulation. We get this from this matrix market from this website. Okay, so now let's have a look. What's this matrix look like? So this is this called Sherman 5, and it's a size 3000 by 3000 something matrix, and this is the sparsity pattern. It's a sparse matrix, and on the right, we did compute the eigenvalues of this matrix, and you can see that the real part of this eigenvalue range from the range is quite big. Okay, it's range from -200 to 600. Okay, with basically no class range. Okay, and you can see that over here at the origin, okay, so there are some small eigenvalues in magnitude. Okay, we're plotting the magnitude. All right. So for this problem, as you can imagine, if we no preconditioning, just solve the original problem and set the tolerance to be like 10 to -10. And say our M, the maximum number of iteration is M. Then you see that over 200 iterations, really not much, the relative residue, nothing didn't go down very much. So not much happening. All right, how can we save this problem? All right, so we need preconditioners. Okay. So the first one we're gonna look at is quite simple. It's called the Jacobi preconditioner, which is really simply just taking the diagonal of original matrix A. Okay, so it's just diagonal value of A. So it's super cheap to apply when you compute M inverse V times, yeah. So it's very cheap to apply. Okay, on the other side, let's have a look at our preconditioned system. So this is the eigenvalue of our new matrix M inverse A, you see that there's no longer any eigenvalues in the left half plane. So everything is positive. I mean, the real part of the eigenvalue, everything is positive. And the range has been significantly reduced. Before was from -200 to 600, and now it's from roughly 0 to 1.5. Okay. And there's a hint of clustering around 1. Okay, so this is very close to 1. And we can see that there are still some small eigenvalues hanging around. But it looks like a lot better, the distribution a lot better than the distribution for the original problem. So let's have a look at the performance. Wow. Okay. Okay, the blue curve is for our original problem, unpreconditioned GMRS solver, and this red one is for our Jacobi. Okay, you see that our Jacobi converges to the desired tolerance in 145 iteration. Okay. Compared to before, really in 200 iteration, nothing happening. Okay. You think, wow, if this simple precondition can be this effective, then how much better can we get if we choose something a little bit more elaborate? Okay, let's have a look. The next example. The next one is called Gauss-Seidel. So again, we solve this. So our Gauss-Seidel preconditioner look like this one, which is just taking the lower triangular part of A as our preconditioner. Okay, simply just taking the lower triangular part of our matrix A. And then on this figure, that's the eigenvalue for this new matrix M inverse A. Okay, so you see that. Okay, so this time we see that there are some definite clustering around eigenvalues around 1. Okay, and the same like for Jacobi, everything is positive. Okay, nothing on the left half plane. Okay. And yep, we can still see some small eigenvalues hanging around. So this one looks like a better distribution than the one we had for Jacobian. Okay, looks a little bit better. So we expect that the convergence can be improved again. Let's check it out. Okay. Okay, so this the yellow one is the performance for my Gauss-Seidel preconditioner. So you see that this time it's achieved the desired tolerance in about 80 iterations. Okay, so you see that by including more information about A in our preconditioner M, the convergence has been improved again. Okay, the first time for Jacobi is really just taking the diagonal value, and then for Gauss-Seidel, I take the lower triangular part of A. And remember that the Gauss-Seidel is still easy to very cheap to apply because it's a lower triangular, so you can just do like forward substitution, you know. So it's still very cheap to apply. Okay. So next one, okay. Next one is called a symmetric Gauss-Seidel. So this time, my preconditioner gonna look like this. It's a product of two matrices, and then M1 is the lower triangular part of A. That's the standard Gauss-Seidel preconditioner, and then M2 is that we take the upper triangular portion of A into the consideration as well, and then just scale that by the diagonal values of A, so that we don't double counting the diagonal. All right, so for this one, you have lower triangular part and upper triangular part, so it will have a similar sparsity pattern to A. And again, this is still very simple, yeah, very cheap to apply. It's really just a forward or backward substitution, okay? But one important thing I really want to make it clear that is that this product, okay, when I talk about M inverse A or M1 times M2, all these matrices with this product, we never form them explicitly, okay? This is very, very important. When we in the code we have, when we always compute, if we compute something like a vector W equals to M inverse, M1, M2 inverse AV for some vector V, and then we always compute the through the matrix vector operation. Okay, so that means like, so instead of forming M1 times M2 and then compute the inverse of M1, M2, we never do that. All we did is really just compute AV first, A times V, that becomes a vector, and then M1 backslash that to compute M inverse, and then backslash it again, M2, and then so it's always matrix vector operation, okay? So we never form any of this M inverse A or M1 times M2 explicitly. Okay? That would be expensive, okay? Okay, so let's have a look the eigenvalue spectrum for this symmetric Gauss-Seidel preconditioner. Okay, but you remember that for illustration, I always compute eigenvalue. We did compute this, but I mean in the code when you do your GMRS, we never form this matrix explicitly. Okay, so this distribution looks maybe better or may not better. It's very similar to the ones for the ordinary Gauss-Seidel. Okay, so let's have a look at its performance then. All right. Okay, so this purple one, this purple one is my for the symmetric Gauss-Seidel. Okay, you see that it converged faster again around maybe 45. Okay. So for this problem, symmetric Gauss-Seidel outperform the ordinary Gauss-Seidel as a precondition. Okay. So I want to emphasize for this problem, okay, so it's for this example, it's outperformed, but no guarantee, okay, it works every time. Okay. So it's really problem dependent.
Chen, a very quick question.
Yeah.
The residuals you've plotted,
yeah,
well, the measurements you've got on the left side, are they the x minus xm's, or are they the residual vectors, if you see what I mean?
You mean this one?
Yeah, it's...
Yes, a very good point. Okay, I will cover that. I'm saving that spot. Yeah, this bit doesn't look right. Yeah, I will fix that in the next slides. Okay. Yeah.
Thanks.
Promise. Yeah.
Sorry.
Good spot. Yes. Okay. So that right. Next example is incomplete LU factorization. So this one is actually incomplete LU made the idea of preconditioning famous in 1970s. Okay, and it's quite often used in practice. So the idea of incomplete LU is to compute an approximate factorization for A. So it's approximate factorization. So L and U are not the exact LU factors, but inexact and sparse LU factors. Okay, so you know that if I can afford to form LU, the exact one, then my problem solved, right? So the problem is that I can't afford to do that. That's why we need preconditioners. Okay, so for comparison, let's still consider the full exact LU factorization of our matrix. So this is the sparsity pattern of my original matrix A. Okay, and then on the right hand side, this is after after the LU factorization. So this is the L part and this is the U part. So you see that a large amount of fill-ins generated by this factorization. Okay, the number of non-zeros before I had roughly like 20,000, and now I have like a million non-zeros. So the number of non-zeros has exploded. Okay, 50 times more non-zero entries after this factorization. So the computational and the memory cost associated with this factorization quickly get out of control for large matrices. Okay. So making it really impractical, okay. Too expensive. All right, so now we move on to incomplete LU. So the idea is very simple. I just want to drop entries from the factorization, and then try to keep the matrix sparse. Yeah, so I know that it's no longer exact. The L and the U no longer exact, but in many cases they are sufficient to use as a precondition. And the criteria for dropping entries can be very simple, or it can be more elaborate based on tolerances. So for now, let's just look at LU 0. So that means that we drop every single entries that would have otherwise filled in. Okay, so this is my original matrix A. The pattern looks like this. And then for my incomplete LU, I want to keep the sparsity pattern the same. Okay, so have non-zeros only in the positions where A has non-zeros. Okay. So that's ILU, incomplete. Okay, let's have a look the resulting spectrum. Okay, if that's my preconditional, then this is the eigenvalue distribution of my M inverse A. Okay, so you see that this clustering around 1, this is nice. Okay, this is nice. There are still a few small eigenvalues hanging around, and so far none of our preconditionals has been able to deal with these ones, but well, that's the problem we have. So okay, but let's still have a look the performance of incomplete LU. All right, so this green curve, okay. Ooh, okay, so our incomplete LU is the winner for today. Okay, it outperforms all the other preconditionals and achieved the tolerance in about 38 iterations. Okay, remember our original size of the problem is like 3,000 by 3,000, right? And now we are solving this, M is only 38. Then we can achieve the our desired tolerance, so that which is great. Right? And then here this is the bit that Gary was mentioning before. Yeah, this part doesn't look right? It looks like Jacobi and the Gauss-Seidel it doesn't. Yeah, so this is because MATLAB returning resvac, which is really the norm, the residual norm of the left preconditional system. So this is the vector I'm plotting. So you remember that this is M. Here we go. Just try to write here. This is M inverse Rm. Okay, take the norm on both sides. Okay. So even at the very beginnings for initial residual R0, which should be just a right-hand side vector B, right? But it will be scaled by this M inverse. For Jacobi, it's the diagonal values, and the Gauss-Seidel is the same. It will be scaled by the diagonal values. So that's why even at the beginning, it doesn't start from 1. So I fix that by calculating the true norm of a residual norm, and then that fix this problem. So bring these two curves back up to the beginning. All right. So of course the main trend is the same. Okay, I'm preconditioned the system that's hopeless, doing nothing over this 200 iteration, and then Jacobi, Gauss-Seidel, symmetric Gauss-Seidel, and then incomplete LU. Okay. Yeah, is that part answered your question, Gary? Is my explanation make it clear? That's the difference between.
Yes and no in a way, because
Okay.
it just realized the other thing I've then realized is you've plotted the residuals, and it makes a difference between the different residuals. But the other thing you'd really want is the rate of the convergence to the solutions, and whether how useful the measuring the residual is an indicator of your convergence to x minus xm, if you see what I mean.
Yeah, I see what you mean. Yeah. So, well.
Oh, well, and another small thing was, while I'm on, these were for left preconditioners. I don't know whether is there very much difference between that and the right preconditioning for this example?
For this example, not much difference. Not much difference. So yeah. Yes, yeah, so it's been left or right preconditioning being used in practice. People have different preference, but yeah. So for here to keep our discussion simple, so I'm just focused on left precondition system, and it's also because MATLAB also just implement left precondition, left preconditioning. So I try to keep the story all consistent. But of course, yes, you can apply it on the right. Yeah. So that means you are solving A, M inverse U equals to B. And then you solve for U first, and then compute X as M inverse U.
And what about the difference between the behavior of the residuals and the behavior of the convergence to the true solution, if you see what I mean? So how does x minus xm differ from the size of Rm?
Okay, I see what you mean. So this need to back to because we are still using this back to here, right?
Yeah.
So because so when you have a preconditioned system, so you are really what we're really doing is like minimize for the preconditioned system, we are minimizing this relative residual. Okay. And then so here again, so the convergence rate of convergence will depend on the new M inverse A or AM inverse, depend on the eigenvalue distribution of this new matrix A inverse M or M inverse A. Okay. So if again, so in the GMRS, if you can bring this polynomial, this polynomial magnitude of this polynomial quickly get down to 0 or something small as M increases, then that means you can converge very fast. And if you can't do that, then okay, then the slow convergence.
Thanks.
Welcome. Okay. So that was incomplete LU, huh? We covered this. Yes, we talk about that one. We are here. Oh, okay. So actually, yeah, my last slides. Just want to summarize what will be been discussed yesterday and today. So to summarize, GMRS, that's its name is generalized minimal residual. Okay, it's a Krylov subspace, iterative Krylov subspace method for solving linear system, AX equals to B. And what we're trying to do is to find approximate solution XM in this Krylov subspace by minimizing the residual norm. And the convergence rate really depends on the property of our matrix A. Okay, the condition number of X, that's the eigenvector matrix, and the distribution of eigenvalues. So really depends on that. And we also covered restarted GMRS. So yeah, it restart GMRS M. So that means we restart every M iterations or M steps to control the storage cost and the runtime. As I see thinking, if we have really large problem, then we just can't afford to build a big big VM. Okay. And it may have a slow convergence. Okay, so which means if we start too early, like M is in the example we had before, that if M is like 40, right? Remember, it's take like 1,300 iterations to finally achieve the tolerance that we would like to achieve. Okay? Or even smaller than that, if M is 20, then maybe it's gonna take a long time forever to actually achieve to get the tolerance down to the ones we would like to have. And the last topic is about preconditioning. It's really essential for most iterative method to be successful. Okay, to improve the convergence. Okay. Yeah, the standard GMRS, remember that he really just behave more like a direct method. Okay, so you really need your M need to be quite big to finally converge. Okay? Yeah, and then here just summarize that we can do left preconditioning and we can also do right preconditioning. And here I want to emphasize that again, remember, we never ever form M inverse A or AM inverse, we never form this explicitly. It's always compute the action of M inverse through a matrix vector operation. Okay, so like M\V. Okay. Yeah, I think that's all my story. Thank you for listening. I'm happy to take questions.
Since I've started asking questions, let me keep going. Could you go back to slide 10? It was the restarted, shows the results for the restarted GMRS.
Yeah. Restarted. This one?
Yes, that's it. So it would look like, I mean, if you restart, you effectively get a repeat of the sort of initial curve from the beginning sort of thing. Every time you restart, you get. So it would look like if you just ran GMRS for a certain number of iterations and monitored the sort of ratio of the, or some sort of, monitored both the cost and the improvement you got, and you looked at some sort of ratio of time or something like this, then you would just get the optimal number of iterations to do, if you see what I mean, before the cost starts to exceed the convergence rate, and then just choose that and just keep repeating that, if you see what I mean. Like, for instance, your remark about 20, from looking at the initial convergence rate, it looked like 20 and 40 would be pretty similar, if you see what I mean. They have pretty much the same convergence rate. It's just that 20 there'd be many more steps, if you see what I mean. But it just looks like you could, from your initial run on a GMRS thing, you could pretty much determine the sweet spot for the number of iterations before you restarted. Just by monitoring the first, you run it for, let's say, 100 iterations, and now you've got an idea of the cost versus improvement for that over that 100 iterations, and you just choose whatever value gives you the best ratio of improvement for cost, if you see what I mean.
Yeah, I think so. Yeah.
So I can jump in and foreshadow an idea along those lines that I can talk about tomorrow, which is like that, but maybe even better, where you would keep some of the best information that you've just generated in your M iterations, so that you don't even have to wait for that initial fast convergence to kick in the next time around. You can kickstart it with information that you save from the work you've just done. So that's along the same lines, but
well, that was my next short question, and I'll stop after that. But
yes.
sure, was just simply, since you've got all these iterations, if you used something different like Anderson iteration to, that was independent of the matrix A, but just a general acceleration process, that if you've got a bunch of iterates, extrapolates them to whatever the best answer is, sort of thing, and it would just seem, so rather than just simply restart, use the previous starting points to just give you a best guess for your new restart point, if you see what I mean.
Yeah, so your instinct about recycling some, or the best version of the information you've just spent all this time working on is very good. And the ideas around this are to do with deflation. So the convergence rate is controlled by the eigenvalue spectrum, as we've seen multiple times in these very slides. So the idea is that if you can get a good read on some of the troublesome eigenvalues, and you can include the corresponding eigenvectors in your restarted space to start with, then you get convergence controlled by effectively the new spectrum without those troublesome eigenvalues in there. So that's the limit of all of these good ideas put together, and I'll talk about exactly that tomorrow.
Thanks.
Can I also ask a question? So, to be honest, I just never saw it in the literature, but still would like to ask, since this is a lecture on preconditioners. So, solving linear systems. So, for optimization person, the next step would be to solve linear programming problems. So, and in fact, it really relies on solving linear systems quite a bit. So, are there some, let's say, semi-standard preconditioners for solving linear programming problems that you are aware about?
So this is where we all have to say, you got to be an expert in your own problem to be able to design very specific, tailored preconditioners. So, Chen Chen's presented some ones to try first that have a good chance of doing okay on more or less any problem. But there's a big art to picking the very custom tailored preconditioners to particular problems. And so the people who are experts on those are the people who know a lot about that particular problem to start with.
So it's the art to creation preconditioners.
Absolutely.
Yeah, thanks. Yeah, that's what I thought, unfortunately.
Yeah,
Thanks.
I mean, the solvers are great, right? The solvers are very well understood and they work great. And so the way to make progress now is to get awesome preconditioners that solve your particular problem.
Yeah.
Yeah.
I guess that's why it's a very active research area to to find a new preconditioner.
Yeah. I think we have a question in the chat actually from Trill.
Yeah, sorry, how do I?
So what I was saying is, it seems like, if I'm reading it right, GMRes 80 is the fastest, but that might not always be the case, right? It depends on the solution. I mean, the smallest iteration gives the least computational cost to calculate because of the matrix, I think, if I understand correctly. So we might expect the smallest to always give the fastest, but maybe that's not always the case.
This is with preconditioning or with no preconditioning?
Just sort of speaking to the slide 8.
Right. Yes. Sorry,
I might have misunderstood as well.
I
Yeah,
have
yeah,
too-
this slide.
Sorry, I have too many things on my screen. The Zoom, so I'm
No,
struggling to find my page number. Oh, yeah. Okay.
Yeah.
Yep.
So I might have misunderstood, but so GMRes 80, that's saying size 80 for the iteration.
Yeah. So I mean, I restart GMRes every 80 iteration.
Yeah. And so I was trying to understand if always a smaller size iteration gave the best solution, but maybe not depending on the matrix, because the idea, because if it's sparser, it's easier to solve with smaller, but if it's bigger, maybe not. I just thought I'd ask and see.
Yeah, so this restart is really like if we really can't afford to, ideally, right, we just do our full GMRes and it converged in 300 something iterations. If we can't afford to do that, and maybe I can only afford to do 80 or 120, then that's all I can do. So ideally, yes, you want to make the M the biggest that you are able to afford, right? The more you build your VM, then you have more information about you get more likely that you can get your that polynomial PM of them, that you can bring that, more likely to bring that down to some small numbers. And then that helps to converge faster, right? If you can quickly bring that down, then you converge faster.
Yeah, okay, cool. Thanks.
Can I ask another question? So very related to this, to Trill's question. So in the case where we don't have a lot of we don't know much about the structure. So what do we do in practice for several applications? You might not have that at hand. So it's best not to restart at all. Is that what the rule of thumb would be? I don't know. In this context.
Well, I never solved the problem that I completely have no understanding about the structure. I have some complicated problem, but I somehow have some idea about the structure, right? So I solve those fractional PDEs, and after the discretization, my matrix A will be a full, not even sparse anymore. It's become a dense matrix. But I have some understanding about the structure, so that way I can. Yeah, I can find build a preconditioner to solve like a simplified version of the problem and use that as the preconditioner to solve.
No, I'm not talking about preconditioning. So this is just restarting of GMRes.
Yeah. Then.
But yeah, I agree, right? So most of the time, at least in things that we do with finite elements and things like that, I mean, you have a sense of what you're dealing with. But I was just wondering, right? So especially for a simple mechanism as restarting. I mean, Tim explained a little bit what you have behind this. It's that you want to preserve some of the information that you have, as much as information as you have.
Yeah.
But sometimes it's not feasible. So I was just wondering if there's something systematic that allows you to say, okay, in these cases you do it, in these cases you can't, which I don't know. So just picking your brain on that.
And then sorry, I have to say I don't know either if I have yeah.
Yeah, no problem at all. Yeah,
I think that's just a hard problem if we really have no idea about it.
Ricardo, this gets back to the point I was trying to make, which is simply that if you're monitoring the first so many iterations, you will see both a sort of convergence rate and a cost. And you can then simply, with those two measures, for any particular sort of restart rate, you can get a rough estimation of the sort of effective. If you look at that curve, for instance, the yellow and green curves effectively just are pieces of of the purple curve, the first part of the purple curve, then just simply repeat it, if you see what I mean, in steps, right? So if you just monitor your progress, I think you'd get a very good idea of where the best cutoff point is and be able to reasonably extrapolate how that particular restart rate would perform as you continue.
Cool. Yeah, understand. Yeah, I agree. That's one way of looking at that, and I think that answers the question. Thank you.
Okay, so no questions. So I guess we can stop here, especially because we're a little bit over time. Thank you very much, Chan. Thank you, and
Thank
see you
you,
all tomorrow.
everyone.
Thank you.
Yes, see you
Bye.
tomorrow. Bye-bye.
Bye.